thank you everyone for coming to attend this talk. I know that the other talk in the nearest neighboring room also looked very interesting. Just to skip to the introduction, it's not really needed anymore, but we work at Deltares both. We are working on Ribasim, which we'll introduce. One of the things I've been active on in the open source community is mostly Julia Geo, which I helped to set up and maintain quite some time ago already. Julian Hofer is going to take over for the second part of the presentation. So let's get started. So, as a lot of you know, water and the Netherlands are very intricately related. We have a long history of working with water, sometimes fighting against water. So, for instance, here on the left, you can see part of the Delta works. And that's a storm surge barrier that stops flooding, and that was created after a large flood killed over 3,000 people in 1953. And so, of course, to build and design these things, you need a lot of knowledge and the ability to model and these kind of large engineering works. So the way that was traditionally done was often to build skill models and to try them out physically. And so the institute that we work on still does that. So this, for instance, here is a wave flume. That's actually the largest wave generator on Earth. So here we can test, for instance, dikes at full scale, at a one-to-one scale. And I just wanted to highlight, we know by now more or less how water interacts with concrete protections. But for instance, now we are more and more trying to build with nature, and for instance, to test how much water does a tree take out of a wave. But what I will focus on is more the whole water system in the Netherlands. So it's large systems, and there are a lot of canals. Here in orange, you can see all the handmade canals. And on the higher side of the Netherlands, where we are, it's a little bit more natural, but still like a heavily altered system. So, of course, it's a large system, quite a complex system, and skill models don't work for that. The only way to really do proper studies on the system as a whole is computer models, and that's what we're working on in Julia. So Ribasim is not something new. Actually, it's already over 40 years old, but we're basically reinventing it from scratch. And that's not because it looks outdated. I think this looks great. But it simply wasn't up to the task anymore of the things that we want out of such a model. So we're rewriting it, and it will be free and open source, or it is already. It's out on GitHub. You can see it. So we're undertaking that. So why Julia? So for Ribasim, this was not really a discussion anymore. It was quite an easy choice, but that was also because of our prior experiences with converting a different model, a hydrological model called WFlow, to Julia. So as you saw in the previous slide, the old Ribasim was actually written in Fortran, but WFlow actually went from Python to Julia, mainly for performance reasons. So as you see here, GitHub tells us that Ribasim is a Python code, but actually it's just 51% Python, and we're always trying to fight to make Julia win, but we just can reuse so much code, so it's hard, even though the entire core, simulation core, is written in Julia. So what's the Python code? That's a package to create the models, to create the schematizations, and a QGIS plugin which allows you to visualize and to interact with the model on a map, basically. Yeah, so we are here. Two other colleagues, Bart and Martijn, are also in the room. Yeah, please come talk to us if you want to know more. So what is a water resources model? So the key thing is that we want to know how much water there is, how much is coming in, and where it's going. And it's not only the quantity of the water that we're interested in, but also the quality is essential, because especially in the lower area of the Netherlands, like salt is a real issue, and that's coming in from the sea or through the groundwater. And if it's too saline, you cannot use it for many purposes. So at the core, the main state of our model is the volume of water in one of these blue water reservoirs, basins. So this is an example of the model. So how large or how small you make the basin is really up to the user. So this is maybe 40 basins, but the model that we're building in a reproducible, automated fashion will probably have at least 20,000 of these basins. And then, so these basins are a component, and there are different components that basically determine how the flow between basins is governed. So these are all components that are part of our physical layer. So this is all implemented in differential equations. But we have two other layers that are active on top of that. So one is a control layer. So that is implemented using callbacks. So this is basically a function that detects a condition and that can change something in the model, in the parameters, for instance, when a certain condition is met. So it can be turn on a pump when it's needed. And another layer that we separate out of that is optimization. So this is all about the allocation of the available water resources. So there are many different users that have demands, and they have a certain priority. So actually the Dutch law kind of dictates the priority in our case, depending on the use case. And the allocation layer basically optimizes the distribution of these of the water. So I mentioned, like in this physical layer, we're using differential equations, solvers, and we have these different components. So for those of you familiar with Modeling Toolkit, it actually allows you to create these kind of models in a very simple way. So for instance, here on the left, there's the code that you can combine existing components together and say how they are connected together. And so a lot of their documentation is using electrical circuits, but there's actually a Wikipedia page on the hydraulic electric analogy, because a lot of these things translate very well to the kind of models that we build. So we were actually initially targeting Modeling Toolkit for a bit, but as I mentioned, we need to scale up to like 20,000 components or more. So when that happens, there's actually a quadratic increase in the compilation time. So this didn't scale enough for our needs. Like now recently, Julia made Sim compiler available, which I think addresses that need largely. However, it's a proprietary backend, so since we have to release this code and its dependencies as free and open source software, we unfortunately cannot just directly depend on it. So what do we use? A lot of packages. This is actually not all of them, But I think at the core, the ordinary diffq package is very important. Like there's a big tradition in our field to write your own solver, and that means most people just implement the Euler, and we get quite poor numerical behavior. So I'm really glad that we can just use state-of-the-art solvers for that. And so all these different components, we connect them using graphs, and the optimization, we are currently using Jump for this. And since we, our main use case, or the way it's being used, is mainly as an application currently. So that means we have to basically load models from disk as like, so we are using files like TOML for the configuration file, and all the data is stored in many tables that we store in a geopackage file, which is SQLite, or arrow files, which is great for large tabular data sets. So if you have large time series, for instance, that's a very good choice. Yeah, with that, I'll hand over to Julian.
Thanks, Martijn. And I even have 80 minutes left. So if you feel that all the problems that I now present is simply because we're using Julia wrong, just chime in. Oh, that's too early. It's replacement of Fortran code. But the one I want to stress here, it's not only replacement of Fortran code. We are taking that to the extreme. If users currently use Ribasim, they don't have to care at all that it's Julia. And I think this is not really the main intended use case of Julia. Like if you have something that is more implication-like, then you have like a single run function, you use it from the Julia API. If you have a library, well, you have multiple functions. But this is not something we can actually do. Like if replacement from Fortran, this is very nice for us. We don't like Fortran, and Julia just provides a nice interactive experience for us. But I find it very hard to convince people to move away from Python, because Python has this big ecosystem. They don't really care about speed, because they have all of these libraries in C. For their scripting use case, Python is perfectly fine, and they want to continue using that. But even if they would use Julia, even if they would accept that, they would still expect from us that we would just seamlessly fit into existing workflows. And that, first and foremost, means that we have to provide a compiled executable. This is luckily possible with Julia. You throw your Julia code at package compiler, and it spits us, at least for us, it spits out a folder containing the Julia runtime, all of the dependencies, as well as on Windows, ribasim.exe. The second use case that we have to address with Ribasim, and I think I need to motivate that one a bit more, is that Ribasim only addresses like the most top layer of this low-resolution picture. It is the regional subcatchment, the distribution network. But especially in the Netherlands, this is often not enough. Like, for example, the groundwater level can be really high. Like, sometimes colleagues joke to me, if you take a pipe and ram it into the ground, like water will spit out. That also means that if your river runs dry, you want to model that with Ribasim, well, you have to kind of account for the groundwater. Ribasim cannot do that. And how this typically works is that you have like one domain model for each domain. So we have Ribasim, the Julia kernel. We have something for the unsaturated zone, a Fortran kernel typically, and something for groundwater. And if you want to couple them, executable doesn't cut it. Because executable, what you can do is you can give it a set of input files, you run it to completion, it runs at the end. What you want is you want something within the same process. And that is solved for Fortran. What they do is they have a shared library. They provide a shared library, which exports a couple of symbols. You share the same memory. You are within the same process. And if it's quint hard enough, like all of these different models, they kind of look the same. So you have an initialize step, you have a time loop, and you have a finalize step. If you couple, what happens is you initialize your two models or three, you start a time step, you synchronize data. It has to be in the same process, also for performance reasons. You do another time step, time step, time step, time step. You always synchronize, exchange data between those two domain models in between, and then you finish. And because it's also similar, no matter if it's a distribution network like Ribasim, if it's a groundwater solver, people standardize that. It's called the basic model interface. And what Fortran models typically expose is a C layer, but it doesn't really prescribe a language. Martijn here implemented a reference implementation for Julia, and everyone can just do it for their own model. You have an interface and implement that. So that's what we did for Ribasim. We have our Ribasim core. We implement like this basic model interface, which is just completely general for all models. Expose the CLI for the normal use case. Use package compiler to build a shared library. DLL on Windows, SO on other operating systems, which exposes a C interface, also the BMI. And because users typically want to do that with Python, we then wrap it with an existing Python package and then sprinkle a bit of Julia on top of it. Because one peculiarity about Julia is that not for each Julia kernel, but for Julia in general, like if you call it from a C API, you have to initialize it. So you have to run like Julia init, and at the very end you have to run Julia finalize or something like that. As soon as you have done that, people don't have to care about Julia anymore. They can use a Ribasim DLL, they use the existing Python wrappers, and then they exchange data. All they have to do, all they have to worry about, is the business logic. Like if I have a distribution network, if I have a groundwater solver, how would I exchange data? That's all they need to know. And this all sounds really good, but that's where the rabbit hole started, for me at least. And I want to give you like an idea how deep that was. Because I was kind of familiar with C. I already exchanged data, but still from a Julia developer perspective, there are a lot of new concepts like thrown at your face. You see here one code example for the basic model interface, which describes how you get the shape of a certain variable. So you give it a name, and it gives you back, of course. Give you back in C means just a second parameter. It gives you back a pointer to the shape. And a lot of things you have to think of if you only use the Julia. On the one hand, error handling is the weird part, because in Julia you just throw an exception. If you want to go through the C layer, you have to catch that. You have to convert it to an error code, return an integer, which is quite verbose. So I wrote a macro, try Z, which does it for you. But then you suddenly have to learn how to write macros. I never had to do that with Julia before. And you have to learn how pointers behave. If you never tried C, you have to find out what a pointer is in the first place. If you know C, you still have to learn how that works with Julia. Suddenly, all the functions are really scary. Like suddenly they're called unsafe string, not string, unsafe string. What does unsafe mean? Like then you have to read the docs. What do you have to do that nothing crashes? Because crashing doesn't mean a nice exception with an error message. It means a seg fault. Like nothing, no information, just random crashes. And because not all of this unsafe function exists, well, suddenly you write your own unsafe stuff. Like I wrote unsafe copy too, but this is terrible. Like I had to do manual byte juggling, count bytes, and then pray that the user will give me an SC string. Like a lot of complexity is involved here. Lastly, compiling is hard. Compiling is okay, I feel like, for other languages, like languages which are designed for compiling. But with Julia, there's a lot of things that you have to learn on top of that, even if you use them, even if you use the Fortran, C, raster, you name it. For once, we often talk about this time to plot, right? Like the things that always get better with the next Julia release. You just have to use the newest Julia, and then it's mostly solved. Still, this is also a problem for these compiled binaries. To me, that was not obvious, because even though it's compiled, you still need to worry about more things, like, for example, this pre-compilation. There's an option in package compiler. If you want your binary to be fast, to not have this high startup time, you have to give it a script. It doesn't have to do a lot, but it has to touch like the relevant code paths. Those are then compiled and integrated in the binary, and this is not a big problem anymore. Also, one thing that we had to find out was lazy artifacts. So I knew that they existed, right? Like those are a thing. But I just assumed that package compiler would download them, because why would I want lazy artifacts for my compiled binary? By default, it doesn't do. So we noticed that you have to, like, certain errors just appeared like the first time, or that he had this high startup time. And more importantly, before we change this flag, because there's a flag to include these lazy artifacts, to make them unlazy, to evaluate them. If you don't include this flag, your binaries will not work on systems without internet connection, which is like a no-go for HPC systems. Finally, the compilation time is really, I don't know, maybe it's just us, I will ask the audience later. But if I compile the shared library, we wait 30 minutes. If I compile the executable, I wait 1 hour. No idea why that is different. It should be the same, I feel. Like, also no idea why it's so long. Also, they're the same, right? Like, the compiled executable and the shared library, like, they share like 99% of the code. But still, I cannot compile them in one go, at least as far as I can tell. Please chime in if you disagree. Also, there's no incremental compilation. Nowadays, we don't change the C layer that often, but when I've written it, I've changed a bit, and I waited 30 minutes to compile it again, and this is a terrible workflow. Binary sizes. I think this is not unexpected that it's more than Fortran. Like, Fortran is 5 megabytes, which is amazing, and this enables a lot of workflows that wouldn't be possible with higher binary sizes. And we have more dependencies, right? We also have to ship Julian. So I predicted that it would be more. I didn't expect 2 gigabytes. It's also weird that we cannot share again anything. Like, it would be nice if it would be only 2 gigabytes and not 4 de facto, because we have to ship both of it. In the end, from the user perspective, I lied, right? Like I said, it's a drop-in replacement for Fortran, but it isn't actually. With Fortran, they had a 5 megabyte binary, now they have 4. Or, I don't know, I guess they had 10 before. Now they have 4 gigabytes. And this is quite a big regression. Before I go to the next slide now, because we have still 7 minutes, how many of you have used package compiler? A few, not too many. And of the ones of you who use package compiler, who of you experienced either, I don't know, compilation times greater than 20 minutes, or binary sizes greater than 1 gigabyte? I think the same number, I feel. At least for the people who are interested in the last part, we have this talk by Jeff. Sorry, I cannot pronounce your last name. Hopefully you will tell us. I tried to find videos, but you never introduced yourself.
You've already given the first 3 sentences of my talk.
Well, I can give you my slides, that's fine. But I also hope you will introduce your last name, now I'm curious. Yes, listen to his talk, I will for sure listen to it. It will mention why this is the case, which I have no idea. Also how to remedy that, like tools, how to reduce the sizes. I also hope that they will help for us. Because this is the biggest problem. Like the compilation time is not such a big deal. We don't touch the C layer now. It's now done. But the binary sizes, these are problems. And in summary, even though I now complained a lot, like my part was the complaining part, we are quite enthusiastic. We don't come from the Python side and try to replace that. Would be nice in the future, but we are basically trying to replace Fortran because it's not only an old language, but because a lot of things are lacking there. Julia is a very attractive choice for us, even with the problems that I mentioned above. And I assume that more of that will come, at least within our company, I would assume in the whole sector. And while we are currently just a Fortran replacement, this is not where we want to head. This is now the first step. We want to be a drop-in replacement, but of course we're not using Julia just to, I don't know, have an interactive development. We would like to have users to use it. And that's where all of you are asked, right? Like the better the ecosystem becomes, the more users there will be, the more attractive it will also be for our internal and external users to use Julia to learn it in the first place and not just for Ribasim. But even while we're just a Fortran replacement, we love the journey, right? We have this interactive development. We can play with it. We can play with the data. If we need something which isn't Ribasim specific, we can dive into this rich ecosystem, like the SciML ecosystem, but also outside of it. And finally, there are things we will hope will improve, like everything related to compilation. I hope there are a lot of low-hanging apples there, because it seems to work for other ecosystems. I assume it will work for Julia too. Finally, there's developer tooling. There are many things that could be improved. Julia is still a young language, and you notice that also with the developer tooling. One thing that I would like to see the most is something like static tooling. I know there's chat. I found it hard to get something reasonable out of it. Also, even if it would be reasonable to use, I think without IDE integration, I still wouldn't use it. So having something nicer here, that would be much appreciated. And that was it. These are our contact data, but just chat us up in the coffee room and at the coffee break if you have any more further questions or anything that needs to be discussed outside of questions. Thanks for your attention.
Super nice talk. I liked both parts, and we have a lot of room for questions.
We do.
So who has a question? Okay, there.
So especially I'm facing essentially the same issues with the package compiler. For this pre-compilation step and the code path touching, how you called it, do you just run your test suite upfront, or what is your strategy there?
So with Ribasim, we basically run what we expose with the executable. So you have a set of input files. It runs to completion, and then it spits out output files. So we just run one model. And this is fine enough for us. So we don't run the complete test suite. That would be overkill.
Thanks.
More questions? Here?
So thank you very much for sharing. So I think it's a very inspiring talk and an application that here in the Netherlands touches everyone. So we're first of all grateful that my house isn't flooded. So thank you for that. But more importantly, I'm kind of curious Deltares is a big organization, right? So I'm kind of curious of the team size that you have, and maybe could you speak about how many folk are really involved? And is this seen as an example for other teams inside Deltares, or what's the future looking like on this front from a developer perspective?
That's a good question. So I guess I should answer because I kind of introduced it at Deltares. Initially, because we don't only build software, but we also do projects. So initially, I was using it in projects where it's really a much easier choice. So now, basically, we have 2 of our models in Julia, and overall that is seen as a good experience. And so with this precedent, they are seriously considering also for other models, especially to use Julia in the future. I think so. My experience overall, because and like the initial blog post about solving the 2-language problem strongly resonated with me looking at Deltares, because we had this kind of culture of like the software engineers using C++, Fortran, and the researchers using Python or MATLAB. So what I see so far is that it's easier to replace Fortran with Julia than it is to replace Python with Julia. Of course, when there's sufficient performance bottlenecks or there's no vectorized code available, it's becoming much easier. But that's my experience so far. But about team size on Ribasim, we work with about 5 people. Not all of them full time. Similar for the Wflow team, for instance. Yeah.
But it feels like the floodgates are open now. So we're getting like a lot of Fortran code. It just was kept around because there's no good alternative. So They said, like, even if we would not replace this kernel, we would just rewrite it again in Fortran, and would it really improve that? And now Ribasim especially is mentioned a lot. And in this context, Julian. And now they're asking, like, could we give presentations about Julian, but also could we give presentations about our experience? One thing is that they do notice is how fast we could spin something usable up. Also because of the ecosystem, like the combination of Julian and the SciML ecosystem. I think this is very attractive for them. Typically, they I don't know, developed like 10 years until they had something feasible enough that they could replace the Fortran kernel from the generation before. So this was always a very big investment. Now that we have this and spun up something usable within 1 year, this is quite attractive to many of our colleagues, and also outside of Deltares.
Maybe just one quick thing, because Jeff mentioned that you were already stealing lines, but I can steal maybe one more that's relevant. So it's not just a direct technical problem, but it's also the ecosystem that basically has to take into account the size of code and data. So for instance, we noticed that the time zones package, which is a very commonly used package, actually pulls in a 300 megabyte artifact. And actually, I think this morning it just got a positive review because we replaced it with a single dictionary, because we actually only needed a small part of the data. So all these little things also help a lot.
Yeah. Like if we want to replace Fortran, we also have to be future-proof. A lot of our software is used for decades. And if we cannot tell them, then what we have to tell our colleagues, even if Julie would die, we could reuse that. And promise alone is not good enough. What we have to tell them, well, these binary sizes are small. This continues to be reproducible. These kind of questions will be important to actually go all in for us.
More questions?
I might as well comment, since thank you. I wasn't expecting such a perfect motivation and setup for my talk. That is, that's perfect. What I will say is, I think the 30-minute and 1 hour compile times, I think is a bug, and I think we can fix that.
That would be great.
I have some theories about what's going on. I think we can fix that. That's just silly. And the other thing I know is that the SciML ecosystem has a really large number of packages. And if you depend on that, that tends to really bring in a large amount of stuff. I assume you're using that in that.
Instance. So we use a lot of dependencies, right? Like we didn't expect this 5 megabytes.
Yeah. So it's that there's just a really big dependency chain in the whole modeling toolkit and SciML ecosystem. So there's a little bit of the problem is intrinsic there, but because that's just a lot of software. I think maybe something can be done to kind of prune more dependencies from that. Possibly there's some things we can do too that I'll talk about in my talk. But so I think there are things we can do. We're working on it.
I mean, something like tree shaking would be nice too.
Yep.
Does someone have more question? Okay. We have a room for one last question.
Hi, your last remark, even if Julia would die, it would still continue, because what I'm coming with a larger history on Fortran packages, and I see them use it in it, and the question is, what about 10 years, what you've done now? How does that survive, and how is it still that investment in this additional software, in these wrappers?
So I had troubles understanding the question. Did you understand it?
You mean
so the question is,
Fortran.
What would be the state, what you did now, over 10 years? Is it still usable? Can people jump in there, or do we got the same battle?
I'm not sure how to answer, because of course I cannot look into the future. But I don't know really. I mean, I don't think clearly that the Julia language will go anywhere anytime soon. but also actually for Fortran, so for existing kernels, even the usage of Fortran and the decline in popularity and the fact that a lot of new students coming out of university are hesitant to program in Fortran is actually seen as a major reason to reconsider the use of the language. So yeah, it kind of works on both sides, this debate about the long-term usage.
Still, I would say it's fair to say that Julia is a risk for us, because we are thinking in terms of decades. We have pieces of software which are 40 years old, or 30 years at least, which is still in use and still supported by our company. So basically everything that increases confidence that it will be usable for a long time to go will improve the situation. Will give us more motivation on top of all of these many arguments that Julia is preferable to Fortran or C++, but mostly Fortran.
Cool. Extra round of applause for our speakers. And yes, we have a small break now. So.